on the morning rain. I used to feel so uninspired, and when I knew I had to face another day, Lord, it made me feel.
Section 1.5 is on multiplying and dividing radical expressions, and I believe this is review. Again, just taking it to a more difficult level, but we did some pretty tough ones last year. And the other thing I know is that we'll do this section in 2 days. Today will be the longer of the 2 days. Alright, when you multiply polynomials and multiplying radicals, I've just put multiplying polynomials because, again, it's quite similar to multiplying radicals. In terms of, you do not this time need like terms. Remember when we added and subtracted polynomials, we needed like terms. We talked about that last day. You cannot add 3x squared and 2x. You have to add 3x squared and 2x squared, and then you get 5x squared, right? So you don't need to have like terms. So even though there's two terms here, 3x squared y is one term, and 4x cubed y to the fourth z is the second term, those are certainly not like terms. You can still multiply them together. Basically what you do is you multiply the coefficients together, the 3 and the 4, it gets 12. You multiply the x's together, so you have x squared, and you're multiplying by x cubed. And the rule is, when you multiply powers with the same base, add the exponents. So you get x to the fifth. Same rule with the y's, so you have y to the 1 and y to the 4. You multiply those, you get y to the fifth. And then you still have the z here, because you're multiplying, I guess, z to the 0 times z to the 1. 0 plus 1 is still 1. So that would be your answer. You don't need like terms. It's the same with multiplying radicals. You don't need like radicals. Again, last day we looked at if you were adding 2 root 3 and 4 root 30, you can't add those together because they don't have the same radicand. But if this was 30 as well, 2 root 30 plus 4 root 30, no problem, 6 root 30. Okay? So you don't need like radicals here. If we look at the first question here, we don't have like radicals. One's root 5, one's root 10. But it's fairly straightforward. What you do is you multiply the coefficients together. 4 times 3 is 12. And you multiply the radicands together. 5 times 10 is 50, and it's still inside a radical sign. Okay? You'll notice that just like up here, the answer has a new term. Right? It was one term was x squared y, the other term was x cubed y to the fourth z, and now you end up with x to the fifth, y to the fifth z. When we added, it stayed the same, x squared, x squared, x squared. Same with radicals. One radical was root 5, one was root 10, but our answer is root 50. And when we added, it stayed the same, root 30, root 30, root 30. Okay, so there's those two differences that you need to worry about. One is that you don't need like terms or like radicals when you multiply and divide, and the second one is that you get a different term once you multiply them together. Okay, we're actually not quite finished this because what you should realize is we always want to simplify. So we're going to do our tree. We have 5 and 10, and then 10 becomes 5 and 2, and this is a square root, so we're looking for a pair. And there's our pair. So we can bring a 5 out, but when the 5 comes out, there's already a 12 there. So what do? We go 12 times 5, 60. What's left inside? The 2. So there's our answer right there. Okay, the reason I left this big space here is to write down the general form of multiplying radicals. Basically what it looks like is this. M and the kth root times n and the kth root of b equals, basically, we're just going to multiply the two coefficients together. If we have two radicals, we multiply the two coefficients together, so that would give you mn. The index stays the same, so it's still the kth root, and you multiply the radicands together, so it'd be ab. This is what you're going to do for all these questions. Now, this relies on both radicals having the same index. What if you don't have the same index? Can you multiply them? You actually can, and we're going to look at that in the second page of this work today, but it's a different method. So the first page and a little bit at the top of the second page, we'll be doing this method where you just multiply the coefficients and multiply the radicands together, and then we'll do some more difficult ones where they have different indices. Indices is the plural of index, right? Okay, so we got this first answer. It was 60 root 2. Let's go on to the next one. Okay, we have two radicals. We're multiplying, so they don't need to be like radicals, and they're not. So we multiply the coefficients together. Negative 4 times 2 is negative 8. And inside the radical sign, we multiply 2x squared times 10xy. 2 times 10 is 20. X squared times x to the 1 is x cubed. We add those together, the exponents, and we still have a y, or y to the 1. Okay, now we're going to simplify this like we did last day. So 20 is 2 and 10, and then 2 and 5. We're looking for a pair, and we do have a pair of 2's. So the 2 comes out, but there's already a negative 8 there. So 2 times negative 8 is negative 16. Be careful, you also have 3 x's. And if you have 3 x's and we're looking for pairs, you can make a pair. So you have an x that comes out as well. What's left inside? Well, there's a 5 that's left inside. There's 1 x that's left inside. And the y can't come out. You needed to have at least 2 and you only have 1. So this is your answer for the second question. We're not going to worry about absolute values and restrictions. We're going to assume, because your book does this as well, that we're restricting the domain to only positive x's and y's. So in that way we don't have to worry about the restrictions, which is very nice. Okay, this looks a little bit more complicated. It is a little bit more complicated. We're multiplying a binomial times a binomial. So you have to remember from last year, how did you multiply binomials times binomials? It's the good old mountains and valleys. So you're going to have to multiply 4 things. Root 3 times 2 root 3. Okay, well the coefficient out here is 1, so you're multiplying 1 times 2, which is 2, and root 3 times root 3. Now, I'd love it if you get to the point where you can do that very quickly, root 3 times root 3. But for now, I will write it. Root 3 times root 3 is root 9. Okay, the next one. 1 times 3 is 3, and root 3 times 2, root 3 times root 2 is root 6. Okay, now we're doing this one. So it's negative. There's a 1 there as well. So 1 times 2 is 2, and root 2 times root 3 is root 6. And finally we have this last arrow here, so it's another negative. Negative 1 times 3 is negative 3, and root 2 times root 2, again, it'd be great if you can do that very quickly, but for now I'll put root 4. So what am I talking about this very quickly thing here? If it's root 3 times root 3, it's root 9, and root 9 is the same as 3. So root 3 times root 3 is 3. Guess what root 5 times root 5 is? 5. Root 11 times root 11? 11. Okay? So what we have here now is 2 times root 9 is 3. Plus, okay, we could combine these two right here, because we have 3 root 6, take away 2 root 6. That leaves us with 1 root 6, or just root 6. And then minus, hey, again right here, we have 3 times root 4. What's root 4? 2. So we have minus 3 times 2. You could have done that very quickly as well when you multiplied here. You did 1 times 3 is 3. Root 2 times root 2 is 2. You should have gotten it. You can do that right away. You don't have to do root 2 times root 2 is root 4 and then do the 2. You can do it in one step, if it makes sense to you. Okay, 2 times 3 is 6, plus root 6, take away 3 times 2 is 6. Oh, interesting. We can combine that with that. If we do that, 6 take away 6 is 0. It's gone. The only thing that's left is this root 6. And that's our answer. Okay, this one. Are we doing mountains and valleys? No, it's only a monomial times a binomial, so it's just mountains. We only have to multiply twice. So 9 times 1 is the coefficient there. And then it's still the cube root. You certainly don't make it the 9th root or anything. It just stays the same. 2 times 4 is 8, and w times w is w squared. Okay, for the second one, 9 times 7 is 63. It's still the cube root. 2 times 28 is 56, and you have a w. And we'll do our tree. 8 is 4 and 2, and then 2 and 2. And we're looking for a trio, a group of 3. And there is a group of 3. Right there's our group of 3. So, I don't know, maybe I'll write it here. The 2 can come out, and there's already a 9 there, so 2 times 9 is 18. We only have 2 w's, and you need 3 because it's a cube root, so you can't do that. The w's have to stay inside, so you have w squared staying inside. Okay, let's do a tree for 56. 8 and 7, 4 and 2, 2 and 2. We're looking for a group of 3. We do have a group of 3. 2 comes out, and there's a 63 there. Oh, it's a big number. So 2 comes out, multiplied by 63 is 126. There's only one w, so you can't bring the w's out because you need at least 3. So we'll write the cube root of what's still left in is a 7 and the 1w. And that is our final answer in that one. Page 2. Okay, here's a binomial squared. This is one of the most common mistakes in high school math. People think you can spread the love here and just do this first one squared and then 5 squared. You can't do that. You can only spread the love with multiplying and dividing. What you have to do is you have to think, if you're squaring this, you're multiplying this binomial by itself. So be very careful. And then you have to do mountains and valleys. All right, let's try to do this the faster way. 4 times 4 is 16. Now, right here, root a times root a. What's root a times root a? It's a. If you don't understand, root a times root a is root a squared, and the square root of a squared is a. But it'd be great if you could do it a little bit faster like that. Okay, the second one. 4 times 5 is 20, and then root a times, well, there's nothing there, so it's root a. Because you could think of it like the square root of 1, I suppose, and a times 1 is a. Okay, the bottom one, 5 times 4 is 20, and you have another root a, and then 5 times 5 is 25. Anything you can combine? Yes, those are like terms. You can combine those. So 16a plus 40 root a. Remember, when you add, you need the terms to be the same, and it stays the same. So it's still root a plus 25. There's nothing else you can combine. You are finished. All right, these next ones involve, if you look down here, involve radicals that have different indices. This has an index of 3, this has an index of 2, so we can't use the method that we just talked about. We need a different method. So the method we're going to use is this. We're going to convert the radical expressions into exponential notation. So this is radical notation up down here. This is exponential notation up here. Okay, so we did this last year. If we're switching this, whenever you have a power that has a fractional exponent, you know you can put this sign, the radical sign. The base, the x, goes inside. This 4 is underground, it's the root, so that goes here. And then the 3 can do one of two things. You can either put on the x, like that, or we could do the whole question kind of the same thing. We could put the x here, the 4 out front, like we did there, and we could raise the whole thing to the third power. Okay, both of those are great. So what you have to be able to do this year is you have to be able to go from this or this, one of these two answers, you have to be able to go back to that. So for example, if I told you there's a radical, the cube root of x squared, and I asked you to write it in this form, could you do it? You should be able to do that. The base, the x, is here, and it's going to be a fraction. Remember, this is the underground number, this is the root, so that goes on the bottom and the 2 goes on the top. I mean, it's a pattern, so you should be able to pick this up. So that's exactly how you're going to multiply these together. You can't just go excuse me, you can't just go m to the 5th times m, because these don't have the same index. So you're going to switch them both. So what's this square root of m to the 5th? What is that in exponential notation? Well, it would be m to the 5 over the little number out here, which is the root, is 2, times m to the, well, I don't see an exponent here, so it must be a 1 over 3. Why does that help us? Because now we're multiplying two powers and they have the same base. And the rule is, when you have the same base, you keep the base the same, so it's going to be m, and we add the exponents. So it's going to be 5 over 2 plus 1 over 3, and that can be our new answer. So maybe over here I'll figure out what that equals. 5 over 2 plus 1 over 3. Adding fractions, you're expected to know this. You need a common denominator. Lowest common denominator is 6. And 6. What do you multiply this 2 by to get 6? 3. Do the same to the top. What do you multiply this 3 by to get 6? 2. Do the same to the top. So 5 times 3 is 15. 1 times 2 is 2. So it gives us the answer 17 over 6. So back here we can say it equals m to the 17 over 6. That's great, but what I want you to do now is to put it back into radical form. So this equals, every time we have an exponent that's a fraction, you know you can put a radical sign. The base goes inside, the root is here, and we're going to raise it to the 17th power. I'll put the 17 in there. Guess what? you can simplify this even more. If you think about it, you have 17 m's, m times m times m times m times m. I'm not going to write all 17. They come out in groups of 6. So how many groups of 6 can you get there? You can get 2 groups of 6. You'd have one group of 6 and another group of 6. Those would both come out. So you'd have an m squared out front. Then you'd have the 6 root of, how many m's are left over? If you have 6 here, another 6, and there were 17 total, you'd have 5 left over. So this is your final answer. That's a difficult question. But if I remember correctly, we did have some questions like that last year. Okay, the last one is very similar to that. We're dividing this time, but you do the same sort of thing. So we're going to switch these. They have different indices. This has an index of 2, this has an index of 4. We can't do that. So we have to switch them into exponential form. The first one on top would be x to the 7 over 2. And we're going to divide it. That's what this line means, divide it. I'm going to write divide like that. You don't have to, but I'm going to. We're going to divide it by x to the 3 over 4. What's the rule when you're dividing and you have powers? If you have the same base and you're dividing, you subtract. So it's going to be equal to x to the 7 over 2 minus 3 over 4. Let's figure out what that equals over here. 7 over 2 minus 3 over 4. Again, you need common denominators. Lowest common denominator is 4. What do you have to multiply this by? 2 and 2. Whoops. And this, you didn't have to do anything. Multiply by 1, I suppose. So you end up with 14 here and 3 there. You end up with 11 over 4. So we get x to the 11 over 4. Now we want to put it back in radical form. Every time you have an exponent fraction, you can put this sign, put the base inside. This is the root, which is underground, so it goes out front. I'm going to raise it to the 11th power. Same as the last question. If we have 11 x's, 4, 5, 6, 7, 8, 9, 10, 11, you don't want to write them all out, but just so you can picture it, they have to come out in groups of 4. There's a group of 4, there's a group of 4. They come out, so it's 1x, another x that comes out. So we have x squared, and then we still have the 4th root of, how many x's are left? X cubed. We did it. We're done. Okay, again, we did this sort of thing last year in the first chapter we did, and it was a very difficult chapter. Hopefully it'll seem a little bit easier this year. Okay, take care.